that we're.
Sorry about that.
No worries. Before I start, of course, I'm going to say that I'm advised by Charlie Conroy, my advisor, and I've worked closely with Anna Venatsa, who just left Harvard for a staff position at Carnegie. And all this work is done within our tight-knit H3 survey team. So having said that, let's get started. So this talk is really going to be about the history of the Milky Way. And galaxies like the Milky Way really build up in a very, very messy manner over time. So in lambda CDM, the way we think galaxies build up is that they're continually assimilating these smaller immigrant galaxies that keep falling in. And with time, the galaxy grows and grows, but across its entire history, it's been taken in these smaller systems. And today, you end up with really this huge mess, right? In this movie here, thanks to Amina Helmi, we are seeing each individual system is given a distinct color. And the stars from each of these systems are completely tidally disrupted and spread across the entire galaxy. And if not for these colors, just by eye, spatially, we really would not be able to tell that, these are all from different systems, except when we see these very recent mergers and you still see they're in the form of these cold streams, you can tell, okay, maybe those stars are together. But in general, everything is super mixed up. And this is something that we expect to have happened throughout the history of the Milky Way. Now, if we look at the Milky Way's merger history in terms of very broad events, in terms of significant mergers, right now we are undergoing a pretty significant event. If you just look at the sky, in the southern sky, you see the Magellanic Clouds. They're on first infall. This is a merger that's happening right now. Both these galaxies are fairly intact. There are some hints of tidal disruption, but largely these really look like fairly compact, undisrupted dwarf galaxies. Then you go slightly further back in time. At about redshift of 0.5, about 5 gigayears ago, we experienced a merger with the Sagittarius dwarf galaxy. The debris from Sagittarius is spread out in terms of these very beautiful tidal streams that are spanning the galaxy in these garlands. And we do observe them as these kind of these streams, these cold streams. And so you can imagine a continuum, right? So we have these Magellanic Clouds that are fairly intact. Stepping back in history, you have Sagittarius, which is more dispersed in terms of these streams. And going even further back, you would expect the debris from these events to be much more mixed along this continuum of fairly intact, slightly more stripped, and completely stripped into these into this debris that's spread all across the galaxy. So in today's talk, what I'm going to do is I'm going to walk you through how we are trying to recover the accretion history of the galaxy, basically identify all these individual colored events that you're seeing in this mess on the screen here. We're going to try and pick those apart into individual distinct systems. And then in the second half of this talk, I'm going to talk about how this view of the accretion history of the galaxy is now informing our understanding of how dark matter within the galaxy is distributed, where has it come from, and what is the substructure of all this dark matter. So the broad idea here is the stellar halo retains a lot of memory. So just a schematic of the Milky Way, we are sitting in the thin disk, the sun is somewhere here, and in this illustration, you see this thin film of stars, this gossamer of starlight around the galaxy, which is the stellar halo. And the record of all these mergers is preserved with very high fidelity within the stellar halo, and this is for two reasons. The first is that the relaxation time in the halo is quite long. So here I'm showing you a simple movie where we will see we're sitting in a sun-like star here, and we're going to see an accretion event that happens. So these are spatial coordinates. And in the right panel, I'm showing you integrals of motion. So things like energy, angular momentum, stuff that we learned back in the day in high school are quote unquote conserved quantities. So in detail, these things are of course not conserved within the Milky Way because there's dynamical friction, but to first order, even when stars from any individual merger are spread out all across the sky in spatial coordinates, they still retain a lot of coherence in these integrals of motion. So here we're plotting energy and angular momentum. The z component of the angular momentum is expected to retain a lot of memory, just because our Milky Way is rotating in a way that the z component of the angular momentum is typically conserved for these kind of mergers. But here the idea is that even though your stars are spread all across the sky from any individual merger, when you look at these quantities like energies, angular momenta, eccentricities, actions, you expect stars that fell in together as part of the same merger to retain a lot of coherence for very long time periods. The other property of the stellar halo that really helps us out to do this kind of science is that stars from the same galaxy share similar chemistry, similar chemical DNA. So you can imagine a more massive merger would be more metal rich, whereas a galaxy that is more like an ultra-faint dwarf galaxy, a very small galaxy, would be more metal poor. You can also go into alpha abundances. So an alpha enhanced system is more likely to have been accreted very early. A more alpha poor system is likely to have been accreted more recently. So you can use chemistry on top of these integrals of motion to really tease apart these various events. But to calculate quantities like energy and angular momenta, you need the full 6D phase space coordinates. So you need all your positions and all your velocities. And to access metallicities and alpha abundances, you need to measure these abundances from high resolution spectroscopy, ideally, to get that kind of precision. So this field has completely changed in the last 2-3 years. So all the concepts I've described till now were really established in the early 2000s with work from Amina Helmi, Catherine Johnston, a lot of others around the New York area wrote all these papers envisioning that this would be possible. But this has really like become reality in the last 2-3 years since the Gaia satellite started giving us these massive data releases for billions of stars. So Gaia is measuring very precise positions in terms of the RA and DEC on sky, and parallaxes in terms of distance to these stars. Gaia is also measuring proper motions and will also be delivering radial velocities for a lot of stars. Further, Gaia is also going to deliver chemistry for a large fraction of very bright stars. But unfortunately, to do the kind of rewinding the clock of the Milky Way and reconstructing the history, Gaia by itself doesn't quite cut it. And the reason for this is that all this fantastic Gaia data we are getting, when you really like look at it in detail, you have access to all these coordinates only in a fairly small bubble, in this small solar bubble around the sun. You have access to this perfect data. And as you go away from the sun into the bulk of the halo where all this debris is, you don't have access anymore to all this fantastic full 60 phase space coordinates plus chemistry. And this really is the motivation for what we're doing at the CFA with the H3 survey. So here's a way of quantifying it. So we think eventually Gaia will have really good parameters for stars brighter than about R or G of 15. But what we really want to do is we want to go to fainter magnitudes to really get the bulk of the halo, to get all these accretion events and their initial debris from when they're falling in to really understand these various mergers. So yeah, that's where we come in. We are the H3 survey. So H3 is, as all great astronomy projects go, we have to have a fairly contrived acronym. And ours is hectoshell in the halo at high resolution. Hectoshell is the instrument with which we are carrying out this survey. So we are we're doing Eshell spectroscopy with very high resolution, so R of about 32,000. And with this spectroscopy, we are measuring radial velocities. We're measuring distances by measuring the surface gravity of individual stars. We're measuring very precise, we're using precise proper motions from Gaia, which are still really good in this magnitude range of about 15 to 18 magnitude where we are targeting. And we've been doing this now for the last 2 years. We've collected about 180,000 spectra. We're planning on doing this for another 1.5 years at least. So the eventual survey, at the end of the survey, we'll have about 300,000 spectra. And these are stars for which Gaia will never really measure these parameters. So this is going to be a data set that we think is going to stand the test of time. And I'll just quickly emphasize why H3 is special in terms of being a halo survey, because there has been a lot of work in this area over the last 2 decades, large efforts. One key reason is that we really get to build on Gaia. So we can have a very remarkably simple selection function. We just select distant stars based on Gaia parallaxes. And that's our only cut. Our only cut is on Gaia parallaxes, this brightness range. We target only high latitude stars because we want to avoid disk, and DEC greater than -20 because otherwise the telescope will break because we're situated in the northern hemisphere in Arizona. And this might sound very trite, but this is actually quite powerful, because in the past, to target halo stars, we've had to make so many deals with the devil. You either have to select extremely metal poor stars. You either have to select extremely biased tracers like BHBs or R. Lyrae that preferentially trace metal poor populations or preferentially trace extremely old populations. But we don't have to do that anymore. We can just make a simple cut on Gaia parallaxes and just get distant stars. So this makes for a very pure selection. And I mentioned this a second ago, but we expect H3 to really stand the test of time, because we really pick up where Gaia is expected to run out of fuel, even at the end of its final data release. So we are at magnitudes fainter than the bulk of halo surveys that currently exist. And we're going to get a very unique sample of distant halo stars. And finally, the most important key feature of H3 is that we are run by a small, tight-knit team that does everything, ranging from preparing the targets, designing the masks, reducing the data, writing the science papers. Everything that H3 has done in the last couple of years has been done by this very small set of 10 folk on your screen. And now I'll discuss one of our key results, which is our anatomy of the galaxy. What is our map of the galaxy, our map of the distant galaxy? So what does the galaxy look like in terms of its various subcomponents? Here I'm going to discuss results out to about 50 kPc. So this is the plot I'll build up to across the next few slides, telling you in detail how did we arrive at this conclusion. But this is what we really wanted to do with the survey. Basically decompose the galaxy into its various constituents, into these various individual dwarf galaxies, and map out what their relative fractions are, map out the extent of their debris. This is what we wanted to do. So let's just look at the data, right? So the data that we want is phase space data and chemistry data together. So here I'm just going to walk you through a couple spaces that we use to perform this kind of decomposition. So here's the energy angular momentum plot that we looked at a second ago. This is the z component of angular momentum. This is the total orbital energy. And we expect things that came in together to be fairly clumped in this space. And you already see, there's a sequence corresponding to the disk. There's a blob of stars here. There's this fairly massive component centered around LZ of 0. So there's a lot of structure already apparent. And then here I'm showing you velocities, radial velocity versus azimuthal velocity, a summary of actions, eccentricities, and then finally chemistry. So we have access to Fe or H and alpha, so mostly magnesium. Is what we are sensitive to. And again, you see the famous high alpha sequence corresponding to the thick disk. You don't really see the thin disk because we are targeting high galactic latitude fields. And you see basically a whole bunch of fairly metal poor stars. If you are used to working with apogee data, you'll realize that the bulk of our data is roughly around where Apogee doesn't have anything. Basically, Apogee runs out of fuel around here. But that's the whole reason we are doing this survey. Again, to make that similar point, that there's a lot of structure in these diagrams. If you just took your ELZ diagram that I've been showing and just split it by metallicity, you see, and here prograde stars fall on the left. So this is the disk, and retrograde stars fall on the right. Interestingly, when you look at very metal-rich stars, there's almost nothing that's retrograde, which is what you would expect, right? Because a lot of because this is the Milky Way's in situ population itself. So most of the in situ stars are on these prograde orbits. Then as you go to like more metal poor regimes, you see a lot of structure starts to show up. There's this blob here, there's this other sequence here, and then there's a lot going on. And then you go to more and more metal poor panels, and you see the space really shifts. And the reason I wanted to show this plot is just to convince you that there really is a lot of structure in this space that we can disentangle using these axes, using metallicities, using these integrals of motion. It's not a hopeless task. We're not just drawing circles around basically like scatter plots. So these are not scatter plots. They really change quite significantly from panel to panel. And just to give you an example now of how we do this for any individual structure, let's look at Sagittarius. It's a famous dwarf galaxy in the halo that we know and love, that we've known since the year I was born in, actually. Sagittarius was discovered the year I was born in. So clearly I was fated to be doing this kind of work. So yeah, if you look at Sagittarius in these spaces that I was showing, people typically select Sagittarius by drawing boxes along the sky, along the stream in RA and DEC. But we now have the privilege of being able to do this very cleanly in these integrals of motion. So our selection is in this space. So it is the Z component of angular momentum versus the Y component of angular momentum. And it turns out Sagittarius is very cold in this kind of diagram of angular momenta. And it just forms this very tight blob. You pick out that blob, and you end up with a very like coherent sequence across all these panels. So you see these very cold wraps that correspond to the leading arm and the trailing arm, respectively, that people have seen in data for the last 20+ years. Now we apply these similar selections and the similar like way of thinking to even other structures that we didn't really know were out there. So here is one structure that we discovered. We think it's a dwarf galaxy. It's a dwarf galaxy that's about 10⁻⁷ solar masses that brought.
Oh, can I just interrupt you for 1 second? I just had a question about your previous plot. So spatially, does this look like the Sagittarius we know if you select only the blue stars and visualize them in RA and DEC? And do you see the bifurcation also from this selection?
That's a really excellent question. So we do see the general structure of the stream. So we wrote an entire paper on this. I didn't include this here, but the reference would be Johnson et al. I'll just post it in the chat. And yeah, so we do see the classic famous structure of the stream. I don't think we can say too much about the bifurcation because H3 sparsely samples the sky. So we don't have like this continuous coverage where we can just like, completely track exactly how the stream's bifurcating. But one thing I'll mention is that in terms of spatial coordinates, we did identify a very hot population in Sagittarius, where you select stars in this angular momenta kind of space, plot them in the stream tracks, and we saw this population that doesn't just follow the cold stream, but is slightly hotter, that we speculated was the stellar halo of Sagittarius, a stellar halo of a dwarf galaxy. So please check out Johnson et al. And yeah, thank you so much for that question. That is indeed something we can do now, where you select things in these integrals of motion, go look at them spatially, and find things like maybe the stellar halo of a dwarf galaxy. So thanks for that question. But yeah, applying the same kind of logic, we are now trying to look for new things. So here's one of the new structures that we found within H3. This is a dwarf galaxy, we think, about 10⁻⁷ solar masses, brought in a few globular clusters with it. And it really stands out as an overdensity in this ELZ diagram, but importantly in the MDF, it really constitutes a distinct population. It has a very like cold peak in the MDF, and you like pull out these stars from the MDF, plot them in a variety of spaces, and they seem to follow these globular clusters. It's very polar. And since we published this paper, it's been confirmed independently by a few other groups. So we basically went through all our data, taking out, first Sagittarius, the other massive dwarf galaxies, looking for what was left, and classified them as being a member of one distinct dwarf galaxy or the other. And we ended up with this kind of census, where the bulk of the galaxy is attributable to about 12-ish structures. So here in this plot, I'm showing you dwarf galaxies that you know and love, like Sagittarius and the Helmi streams. And there's also a bunch of new structures like Wukong that I just showed you, and Gaia sausage enceladus, which has been one of the biggest discoveries since Gaia. I'll discuss this in gory detail, so hold on that one. But we also discover a lot of these other smaller dwarf galaxies like Thamnos and Sequoia and Ether. Which brings us back to the figure I opened with. So what does the galaxy actually look like? What does a distant galaxy actually look like in terms of these individual constituents? So it turns out a galaxy that was accreted at redshift 2-ish, that is called Gaia sausage enceladus. This is not my name, so I will not collect any brickbats for it. Was accreted at redshift 2 and really comprises the bulk of the inner halo. Then there's Sagittarius, which was accreted fairly recently, and it really takes over from GSE in the more distant regions. And then interestingly, in the inner galaxy, we have our high alpha disk that we've known about for a while. But then there's this other component that we call the in situ halo. So these are stars which are essentially identical to the high alpha disk, to the Milky Way's thick disk. But they are on halo-like orbits, and they go fairly far from the plane, and they're very hot. So this is a component that we call the in situ halo. So if you look around the sun, right? So we're basically, I guess we're not on this plot, 0-ish kpc. The bulk of the halo is really comprised of the in situ halo and GSE. But when you look at the halo as a whole, when you look at the distant galaxy as a whole, it's really these three components that comprise about 75 to 80-ish% of the galaxy. And this is a very clear vindication of basic lambda CDM predictions. So for a while now, lambda CDM predictions for the stellar halo have predicted that this is what it should look like. It should be only a handful of dwarf galaxies that comprise the bulk of the halo by mass. And here we really finally very clearly see this, that this is indeed the case. There have been many, many theories for what actually constitutes the distant galaxy and the stellar halo. There have been theories about dissolved globular clusters. Maybe there's outflows from the galaxy that populate the halo. Maybe there's many, many, many very small ultra-faint dwarf galaxies. So there's been a whole multitude of theories, but we really can clearly say that the basic lambda CDM prediction does hold, and it's only a small handful of dwarf galaxies that comprise the bulk of the halo. Of course, the smaller systems are fascinating for a whole wide variety of things that we'll get into in a bit. You can also make a plot like this, where you just look at all the stars that have been accreted versus the stars that are in situ. And here I'm classifying stars as in situ as those with chemistry that are identical to the low alpha and high alpha disks of the Milky Way. So just based on chemistry. And you see that the in situ component of the galaxy is really limited to about 10-ish kpc off the plane. And this is a completely independent constraint on the merger history of the Milky Way. Because if you go look at simulations, and if you've had a very violent accretion history, then your disk gets very disturbed. So your disk stars end up being flung far from the plane. But that's not what we see in the Milky Way. In the Milky Way, we see that our disk is fairly, the disk stars are fairly well contained within a few kpc off the plane. So this is a completely independent constraint that our merger history has been fairly, has allowed our disk to grow in peace. without battering it again and again. So that's something that comes out of this kind of plot. We can also look at the galaxy in chemical space. And one very surprising thing we find, so here in this plot, I'm showing you FEH versus alpha. And here each symbol is sized by its relative mass. So you see the Redshift2 merger, the Gaia sausage enceladus merger is sized the highest because it constitutes the bulk of the halo. Then you are followed by Sagittarius, followed by a lot of these smaller systems. And if you just integrate by I, you see the halo is actually quite metal rich. And this is a conclusion that we were really able to make with H3 very clearly, because remember, our selection function does not make any cuts for metallicity. It does not follow only BHBs or R Lyrae. It's a very simple parallax-based cut. So we can really make this statement with a lot of confidence. And this resolves a long-standing tension about whether the Milky Way stellar halo is weird or not. Because people used to make plots like these, where you plot the metallicity of the halo versus the inferred mass of the halo. And the old metallicity of the halo that people derived from a wide variety of surveys that made all these different cuts to get at halo stars ended up plotting the Milky Way as being very metal poor. And now we also have a good grip on the mass of the halo from things like star counts from the Apogee survey, for example. So this would have put a very low metallicity for the Milky Way's halo would have put the Milky Way in very strong tension against the mean trend that we see across a variety of extragalactic halos and also predictions from lambda CDM simulations. But with this new measurement, the Milky Way really is extremely representative and really follows the mean trend quite well. So that's something that we are uniquely able to conclude with this survey.
What were the ghosts?
The ghost survey is, I think, a survey with HST targeting extragalactic stellar halos. I don't know the exact galaxies targeted. I'm sorry, off the top of my head. So it's a survey that produced all these data points that's run with HST. And then here's a result that that Sarah was teasing at the beginning of this talk, that when you look at all the various accretion events that we have unearthed in the Milky Way, it turns out that all the globular clusters in the halo, the globular cluster streams in the halo that Sarah and Anna study, they seem to follow the distribution of the dwarf galaxies that we've unearthed. So here in this plot, we're plotting all the Milky Way streams for which these 60 phase space positions are available on top of the H3 survey data. And what we find in this paper that we put out around Christmas last year is that they seem to follow basically the dwarf galaxies that we unearthed in our inventory. So the globular cluster streams seem to have originated from these host dwarf galaxies that we've identified. So what we've ended up with is a very neat unified origin story for the vast majority of objects that are in the distant galaxy, which is super exciting because this is precisely what folks writing those visionary papers in the early 2000s had always envisioned, that you would be able to trace back each of these events back to their host systems. Now I'm going to switch gears a bit. I'm going to focus on one particular event. So I'm going to focus on this Redshift2 merger, the Gaia sausage enceladus merger. And the reason I'm going to focus on it is if you want to understand dark matter within the Milky Way, if you want to understand how dark matter is distributed, what its dynamics are, how you can design novel tests of dark matter based on that, you really need to know where it is. And we now know that a large fraction of the Milky Way's dark matter came in with these distinct mergers. So we want to be able to model that in detail to back out all that substructure in the dark matter. So now we're gonna talk about this system for a bit. So the last major merger, and I really capitalized last major merger because it has been referred to with that name for the last many decades. So many phenomena across the galaxy, for example, the formation of the thin disk or why there is a thick disk, have been attributed for the longest time to the quote unquote last major merger. But in the last 2 years, very rapidly, we have come to consensus that this last major merger has finally been identified. It's been identified and it's been named the Gaia sausage enceladus, the GSE merger. And the lines of evidence for this merger really began with this paper from Vasily in 2018, where Vasily noticed that there was this sequence of very eccentric stars that defined this kind of ellipsoidal shape in this VR versus V theta plane. So Vasily was plotting the radial velocities of stars versus the azimuthal velocities of stars. And he found that there was a large population of stars that is consistent with basically being on entirely radial orbits. So that is the beginning of this thread of inquiry. And since then, there's been so many different lines of evidence where we've found globular clusters also follow these orbits. There's a large number of globular clusters that follow these orbits. In terms of chemistry, these stars define a very coherent sequence that is very characteristic of dwarf galaxies. We've seen a break in the halo profile that might be linked to this merger. And this whole story is tied together by simulations where indeed the debris from massive mergers that happened very early in the history of the Milky Way end up on exactly these kind of orbits. So the vast majority of work on this last major merger have been done within this solar bubble where you have a lot of great data from Gaia. And the unique thing that we add in with H3, of course, is we really are able to study this merger all the way out to its epicenter, all the way out to how large the Milky Way was back in the day at Redshift2 when this merger happened. So that's what we're able to do with H3.
And Rohan, sorry, remind us, what's the main argument for why we think it happened at Redshift2?
I'll show you in a second. That's a very great question. So I would say H3 actually has the cleanest, clearest constraints in terms of why it happened at Redshift2, and I'll show a couple plots in a second. But here, I just want to motivate that H3 really gives you an entire census of this very important event in the history of our galaxy, all the way out to the distances we want to be studying this at. So here's a paper from Anna last year, where we are plotting this FEH versus alpha space. So this is chemistry, and we are showing you slices of eccentricity. So in the topmost panel, we are looking at very circular stars. So stars on very rotationally supported orbits. And here you see both the disks. As you go to eccentricities that are higher, so more radial orbits, you start losing the thin disk right away. So you lose the thin disk right away between these two panels. And then eventually you lose most of the high alpha disk as well as you go to higher and higher eccentricities. What becomes prominent in the highest eccentricity bin is that there is this metal pore sequence that runs along this axis. And then there's also a population of stars with high alpha disk-like chemistry, but on these very eccentric orbits. And indeed, these two populations are what we think correspond to the in situ halo, so stars from the disk that were kicked up by a variety of mergers, and from this last major merger at Redshift2 is what we attribute these two sequences to. And one might ask, okay, so there are like a bunch of metal pore stars that seem to be in this kind of sequence. How do you really know it's all from a single dwarf galaxy? How do you really know it's from a merger that happened at Redshift2? These are natural questions. And this is something we can answer in great detail with X3, right? So we can trace the extent of both these components clearly. So this is a plot I've already showed you. So we can really trace exactly where the debris from this event ends. And what we find from a variety of simulations and arguments is that if you take the disk about 10-ish gigayears ago and you perturb it with this kind of dwarf galaxy, you do expect stars to splash up to a certain distance. And that distance really matches up with what we find for both these components. More directly, if you looked at the NDF of stars that are eccentric, Okay, so the eccentric stars I was showing you earlier, if you just plot their MDF, you see that it's remarkably unimodal and can be fit very consistently as a single population with chemical evolution models. So you don't see many different modes in this MDF. You don't see multiple different subpopulations. You see that it's consistent with basically being one thing. And this didn't need to be the case.
Sorry, Rohan, what's MDF?
I'm sorry, MDF is metallicity distribution function. It's just literally a histogram of your iron abundance.
Okay.
Yeah, sorry, my bad about the jargon. So yeah, it's just a histogram of your metallicities, and you see that it's consistent with basically being one component, right? Because if you imagine there were many different radial mergers, you would perhaps end up with a bunch of various bumps in this plot, right? But you don't. And in the background, I'm showing you the entirety of the population, and you do see an example of what I'm talking about, right? You see multiple bumps here. One bump corresponds to the high alpha disk. The other bump corresponds to, indeed, this merger itself. But we don't see any of that. You see this single population that we can model very easily with simple chemical evolution models. Now, the timing of the merger, we can really back out a super precise time for when this merger happened based on ages of individual stars from this population. So we can plot histograms of ages of main sequence turn-off stars, very precise ages down to about 10-ish% precision. And you can also plot ages of stars that were kicked out of the Milky Way disk during this merger, we think. And you see that basically for GSE, so here I'm showing you models, not the raw data. GSE is basically consistent with being quenched at about 10-ish gigayears. And then it still continues along this merger, like kicking up more stars out of the disk. And the merger lasts, we think, for about 2-ish gigayears. And then the merger was done. So from H3, we've gotten very precise constraints on the exact timing of this merger. So basically, we think GSE fell into the Milky Way about Redshift2-ish, and the merger was completed by Redshift1-ish. So this is a very precise constraint on when everything went down. Another thing we found with H3 is the initial orbit of this merger that is very evident in the very distant debris of the galaxy. In the very distant, very high angular momentum population of the galaxy, we see that there is a population that we call Arjuna in our initial papers that essentially follows the chemistry of GSE. And then in later papers, we identified Arjuna as basically being the retrograde debris of GSE that was stripped as it was just falling into the galaxy. So with this constraint, we really are getting at the geometry of an event that happened 10 gigayears in the past, right? That I personally still find this quite mind-blowing that there was this cosmic car crash that happened 10 billion years ago, and we are able to say things about what the geometry of that cosmic car crash was. So yeah, that's something we've backed out of the survey. So I was inspired by all these constraints that we had collected on this very important last major merger to come up with highly tailored simulations of this merger. And this work was really inspired by what was done with Sagittarius about a decade ago by Rohan Naidu and others who got all this 2-mass data and got these exquisite constraints on Sagittarius, and then ran a lot of merger models to try and really figure out what the geometry of the merger was, how much dark matter came in with Sagittarius, and all sorts of fascinating constraints followed from that. So I was like, okay, so they did that with Sagittarius. I'm going to do it with the Redshift2 merger. And that really was the motivation for this project. So what I did was I ran these fully live n-body simulations with Gadget with a really high resolution, 10⁴ solar masses per particle in this simulation. And so I just took all plausible parameters that could have existed for this merger's geometry. And I just ran a huge grid of simulations that I thought could be plausible. And this is roughly what this exercise looks like, by the way. You just continually take a smaller galaxy and crash it into the Milky Way at a variety of geometries. So here I'm just gonna like show you a bunch of movies for how this exercise went down. So for like a few months of my life, I was basically staring at a collection of movies like this and trying to figure out what actually looked like the H3 data. And it turns out that with the constraints that we have found on this merger from all the data that I was showing you earlier, we really can back out a very precise set of parameters that correspond to what actually went down. So here I'm showing you a grid which probably has the highest carbon footprint within a single plot that you have ever seen, because each tiny square on this grid corresponds to one of these very high resolution merger simulations that was run for 10 gigayears. And here I'm coloring each grid point by how likely it is based on the constraints that we have. And this is a grid of the circularity of the satellite falling in versus the inclination of its orbit. And each row here, each vertical column here corresponds to a particular galaxy size. So these galaxies are 1.5 times the stellar mass size mass relation. And here I'm showing various masses. So I tried a variety of stellar masses for this satellite and zeroed in on a configuration that matched all the data that we had really explicitly. And that configuration basically looks something like this, right? So it has a stellar mass that is comparable to basically the SMC today. It has a dark matter halo mass that is 2 times the LMC. So it is the most massive satellite we ever accreted in our entire history. The orbit and inclination that it was accreted along are inclined with respect to the plane, so at a 15-degree inclination to the plane, and the initial orbit was fairly circular, intermediate circularity, 0.5 circularity, which is exactly what you would expect on average from cosmological simulations. The broader point is that when you account for this last major merger, along with Sagittarius and the LMC, they constitute about half of the Milky Way's present day total mass. So half of the Milky Way's total dark matter came in these 3 distinct events. And there's been a lot of work done in the last few years now, including this, that shows that the dark matter from each of these distinct merger events is arranged in very idiosyncratic ways. So it's not just sitting in some nice spherical symmetric distribution that we are used to using in all our calculations. There is a lot of structure that is basically a function of the geometry of these mergers. So for example, in this movie, I'm showing you the YZ plane. So this is just Y versus Z in our galaxy. And you see here, I'm showing you stars from the merger simulation. And you see they really are arranged along a particular axis. It's not just a symmetric blob that looks like a diffuse sphere, right? Like there are shells. There's a lot of structure, and that'll become important in a second as we start to talk more about the dark matter halo. But still focusing on the stars, just to convince you that this really is a pretty decent set of simulations. Here's the data that we are trying to match against from H3. This is the distribution of angular momenta, and by design, this model really matches this up very well. You get out the famous structure that Vesely first saw this quote unquote sausage structure in the radial velocity versus azimuthal velocity plane. It also matches the spatial distribution in terms of distance that we calculate from the H3 survey. But more importantly, and really inspiring a lot of confidence, this simulation also matches a variety of constraints that we did not specifically set out to match when we were selecting our quote unquote best model. So most notably, it really reproduces the density profile of the halo, not just within the H3 footprint, but integrated across the entire sky, which is a very robust independent check on what we are doing. It also gives us a lot of information about the exact geometry of the merger. It tells us when and where the pericenters happen, when and where the apocenters happen, the distances that they happened at, and we can now use this to interpret a wide variety of Milky Way data. For example, in recent years, from, for example, Gaia R.R. Lyry, people have realized that the bulk of the stellar halo is arranged in a triaxial shape. So I like to call it a blimp shape or a Zeppelin shape because of this plot here on the right that I've made. And the vast majority of the stellar halo, as we discussed earlier, is really GSE. So these simulations are helping explain why the inner halo is arranged in this triaxial blimp kind of shape that very, very strikingly has its major axis sticking out of the plane. So the major axis of this blimp is at about a 20 to 35 degree tilt out of the Milky Way's plane. And this is only stars, right? So we are focusing on the stellar halo. And I'm just making that point again, just in 2D projections as well, that you really see this tilted shape of the stellar halo. And this is something that our simulations reproduce very well, even though we never set out to do this. Got it, Sarah, thank you. And when you try to explain where the shape comes from, it really comes from looking at the orbit of the satellite in our simulations. So at time t equals 0, the satellite falls in here, it goes down, it goes up again on top of the plane, and then most of the debris is stripped between these two final apocenters. And the line connecting these two final apocenters is exactly the major axis of this blimp. It is the central spine along which the stellar halo is distributed across. So again, we are really backing out the geometry of this event that happened 10-ish gigayears ago to such a level of exquisite detail. And now the final point I'll make in this talk has to do with these two famous overdensities that we've known for 20 years now, the Hercules Aquila cloud and the Virgo overdensity. These are two really massive overdensities of stars that you see spanning across several degrees of the sky. One of them below the plane and another of them above the plane. So here you see Hercules Aquila cloud. It's this huge blob of stars. This is Z, so Z is how far off the plane you are. And so this is below the plane here. You see this overdensity, the Hercules Aquila cloud. And then above the plane, you see this other famous overdensity, the Virgo overdensity. So this is at distances of about 10 to 30 kpc off the plane. Now, it turns out in our simulations, we didn't set out to reproduce this, but this falls out quite naturally. So you end up with an analog of the Hercules Aquila cloud in the exact position as we see in the data. And you end up with an analog of the Virgo overdensity exactly where we see in the data. And this is super exciting because people have tried to explain the origins of these overdensities for a while now. And there was a sense that indeed these are stars that originated from the last major merger, but the simulation really very clearly shows how you can tie these two overdensities together. And then we have a very simple interpretation again for why these overdensities are produced, why these two huge features across the northern and southern skies are produced. Once again, looking at the orbit of our satellite, just tracing its path and seeing where the debris was stripped. It was stripped between these two final apocenters. These are exactly the stars denote where you end up with the VOD and the HAC. So once again, we really are matching the geometry of something that happened so long ago. And just to give you an intuitive sense of what's going on here, right here on the left panel, I'm just showing a YZ projection, slicing out the portion of the debris that is above the plane, far above the plane, and the debris in purple is far below the plane today. Okay, and then when you plot it in XY, you see this huge cloud of stars. Above the plane, you see another cloud of stars that's diametrically opposite. And these two overdensities above and below the plane are basically trading spots. So every 500 megayears, the huge cloud of stars that is under our feet becomes the huge cloud of stars above our heads, and vice versa. And now, fascinatingly, it turns out that the tilt in the stellar halo that I was talking about is also seen in the dark matter halo in these simulations. And it's most evident in the YZ plane here. Here, I'm just plotting a contour plot of the dark matter component of my simulations. And the dark matter is tilting in exactly the same geometry as the blimp, as the Zeppelin, as the Hercules Aquila cloud and the Virgo over density and the entire stellar halo, okay? And this constitutes a very large fraction of the Milky Way's total dark matter halo mass. It's about 20+%. Because it's not just the dark matter from this merger itself, but also the Milky Way's own in situ dark matter that is tilted out and excited into the same direction out of the plane.
What is the color code? How contrasting is it?
So these are, I think, sigma intervals. So I'll have to double check. I'll get back to you on that detail later. But it's, if I'm not wrong, it's just 1 sigma, 2 sigma, 3 sigma, and so on. But what matters here is the shape, right? Because the bulk of the mass is actually contained in these inner regions.
I'm just wondering how cuspy it is. It's looking like it's quite cuspy, if I've understood the plot, and I was a little surprised. But it depends on how, you know, how rated it is. You can tell me later.
Yeah, I would say the bulk of the mass is just contained in these in the inner like few contours. But what matters for our discussion here is the fact that there's a shape to it, and the shape is not symmetric. So you might be like, okay, so I don't believe your simulations. There's a whole variety of reasons and physical processes that are not accounted for in my simulations. For example, there's no gas, and gas is certainly important for understanding the evolution of the Milky Way. So to that argument, I basically say that one of the most compelling pieces of evidence that we have for this tilt in the dark matter halo is the fact that these two overdensities exist today, the Hercules Aquila cloud and the VOD. So here I'm showing you again in the simulation where exactly they are. There are these two clouds of stars that are on either side of the plane, one at high galactic latitude positive, another at high galactic latitude negative. And the reason their existence is such a strong piece of evidence for a tilt in the dark matter halo is as follows. You take your favorite Milky Way potential, your axisymmetric spherical Milky Way dark matter potential that we've been integrating orbits in for the last many years. You take stars in these two overdensities and you compute their orbits and see where they end up. And in a very short span of time, this very tilted shape of the stellar halo that we measure and these two overdensities that we see are washed out. They basically are spread out in this very spherically symmetric kind of distribution in a matter of like 5 gigayears, and you already start seeing that on the order of like a few hundred megayears. But when you add this tilted component, 20% of the total mass of the Milky Way, you align it in this tilt, and you see that these structures are preserved. They end up being quite long-lived. So you see the tilt is preserved across 5 gigayears. You see the tilt across 500 megayears. And that is indeed what we see in the halo today. Now there's two possible interpretations, right? So one is these two overdensities and this tilted component of the stellar halo is very young, on the order of a few hundred megayears. Or the other conclusion that I'm steering you towards is that the dark matter halo must be tilted. Because again, right, if you take the stellar halo, which we know now is arranged along this ellipsoid, direct measurements. If you take the HAC and VOD, these two clouds that we know are on opposite sides of the plane, arranged along this tilted axis, you integrate their orbits, you end up with something like this spherical blob when you're doing it in your classic Milky Way potentials. But when you account for this tilted component, you end up preserving the shape of the halo. So there's two implications, right? There's two possibilities. One is that these two events, these two overdensities, this tilted component and the stellar halo must be very young because it hasn't been washed out into this kind of blob yet. The other implication, which I'm trying to push you towards, is that actually the dark matter distribution of the Milky Way is tilted along this very axis. And we can test this, right? Because we can go measure ages of stars in these overdensities. And indeed, what we find is that the Virgo overdensity and the Hercules Aquila cloud, these two overdensities, have chemistry that is indistinguishable from the last major merger. That's what I'm showing you in this plot here. So there's really nothing you can't really tell apart these things as being different things. And not just in metallicity, but I'll also add even in alpha, even in their magnesium abundances. And then, of course, we have detailed age information from individual stars of this last major merger, showing that it is indeed very old. This merger happened a very long time ago. And then from some of the plots I showed you earlier as well, we know that the Milky Way has had a fairly quiescent recent merger history where its disk has not been pummeled by these kind of massive radial mergers. And so I would say I strongly favor, I would say the first option presented here is quite implausible. And indeed, you need a tilted component in the dark matter halo to make this work. And this, of course, has a very, very wide variety of implications. It impacts the orbits of every single thing that we've calculated in the inner halo. If you care about stellar streams, if you care about orbits of globular clusters, they're all altered in subtle ways. And we're already finding very exciting results about gaps in streams and the identities of the things that punch those gaps. We'll have to recalculate the local dark matter density. We'll have to recalculate pretty much everything that has been inferred about the inner galaxy, assuming axisymmetry. And that is a very, very long list of things. So exciting times ahead. So yeah, that's all I've got for you today. Thank you so much for listening. This is my summary. I'm very happy to take questions. Thank you for having me.
Thank you very much, Rohan. So I think I'll start by asking the room, 9:40, if you have any questions. I'll leave some time for people to think on Zoom. Or I'll start if no one has a question. Cool, Rohan, yeah, I have many questions, but we're meeting after, so that's great. One of them was, I was curious now, your tilt of the halo, even in dark matter, without the LMC, even though I asked you not to talk about the LMC because we have a guest next week talking about the LMC. I'm just curious because I thought the LMC actually was supposedly playing a big role in that tilt.
No, so in my simulations, right, I do not account for the LMC yet, and that is something we totally should in the future. So you end up with this tilted component. So this merger happens at Redshift2, and this axis is defined shortly after. The LMC is much more recent, right? And most of its effects, it seems, are very prominent in the outer halo, beyond about 40, 50 kpc. Mm-hmm. And the mass distribution in the inner galaxy prior to the LMC's infall seems to readjust to the new barycenter of the setup once the LMC falls in. And so this tilt that we are deriving and seeing in the Milky Way halo, like we see it in the data, right? So it exists today, and we see it in the simulation as well along the same orientation. So it seems that the LMC merger for sure has completely shaped the entire galaxy, but everything I've discussed today seems to basically hold along with that and does not need to rely on the LMC for this to be used. But I absolutely agree that a major step forward is to simulate all these things in the same suite of simulations, and that's something I'm hoping to do as a postdoc. So if there's something that you're excited about, yeah, then hire me, please.
Cool. I guess I will ask one more question. So I was curious now the timing of the GSE merger from the quenching argument, which is quite convincing. So I'm just curious to see if I got it right. So you're saying that because the dwarf galaxy that fell in couldn't form stars after it fell into the halo because it's supposedly quenched, that's why you can age state back to those stars, right? Cool. And then my question is just, how uncertain is that? Because I'm thinking maybe these types of dwarf galaxies have starbursts in their like pre-infall, and I guess it's not that important at the end if it's like Redshift 2.5 or Redshift 2, but is that something you've thought about in terms of the timing argument?
Yeah, no, that's a really excellent question. And I'll say that, so these systems are extremely gas rich, right? So like ridiculously gas rich. So gas rich in a way that would strike us as quite bizarre, like today, right? So their stellar mass, we think, might be even lesser than their gas mass. So
you don't mean today, originally when they fell in.
Yeah, that's right, at Redshift 2. Today, it's all completely disrupted. Today, we only have...
That's purely theoretical, right? You don't have direct evidence for that.
We have direct evidence for typical Redshift 2 galaxies out in the field that we've measured. Not this.
Okay, great.
People have tried to fit chemical evolution models and said that, but I don't think we have very strong constraints on the gas mass of the system. But yeah, no, so the quenching argument lines up very well with a figure I didn't get a chance to show, but I'm just going to pull it up anyway. It lines up very well with the dynamical arguments from this simulation. And so see, there's the in situ halo, right? So it's the disk stars that have been kicked up from these various mergers. And then there is GSE itself, that we have the age distribution that abruptly truncates around here, and there's like there's a short tail that follows in the data, but we really can model it as being due to observational uncertainties. And the very curious thing is, why is there a 2 gigayear offset between the truncation of the star formation history in the satellite and the truncation of the age distribution in the in situ halo? So these are stars kicked up out of the disk, right? And it turns out that if you match up from our fiducial model, the various pericenters and the timing of the merger, it seems that the galaxy started quenching at around its first pericenter, is when you saw this major quenching happen. And then you still have the merger go on for a couple gigayears. And that offset very nicely lines up with what we see as the age distribution offset between these two components. So that's giving us a lot of like confidence in concluding the timing, because we got these two very independent ways of looking at this. One is from pericenters from these models, and the other is from just looking at the ages directly measured from the data.
That is very cool. I can see Mike Lanson is saying any dwarf galaxy in the field will have high gas fractions, I guess observationally, can be many times the stellar mass for these smaller galaxies. So I guess that is an uncertainty to know exactly what it came in with, but yeah.
Yeah, I was just
I'm just saying that's not a weird thing to assume, right?
Yeah, okay, that's what you're trying to say.
Yeah, no, not at all. I was just trying to get to the point that at Redshift 2, things were just much more gas rich than they are today on average.
Yeah, that's true too.
Yeah. So yeah, we feel pretty confident about this timing argument, but I will acknowledge that there's a lot of debate right now in the literature about this, and people are trying to figure this all out, but we think we have a pretty good unified story for why exactly this happened.
Yeah, it's cool that your different stories kind of match up with this one simulation. Okay, no one else has raised their hand, so I'm going to ask one last question. Since, oh, sorry, one person. Go ahead, Moshe.
Yes, to what extent, if any, does our new understanding of dark matter distribution shed any light on dark matter interactions, like dark matter clumpiness, dark photons, or any other feature?
Thank you. That's a great question, and it's a direction I'm hoping to head in the future. Right? There's a variety of tests that people have thought up very cleverly for several years, and there's many of these experiments that have been running, trying to test, the exact particle nature of dark matter and stuff. And a critical input that goes into many of these experiments and things is, what is the velocity distribution and what is the actual distribution of DM in the galaxy and around the solar circle, for example. And my hope is that this is basically a first step in the direction of really building out much more realistic models to do that kind of work. But this work by itself has not placed constraints on any of those really fundamental questions yet. But I see it as the first link in the chain that leads to more of that detailed work.
Thanks.
I have a question, Sarah. But
Yeah, go ahead, Glennis.
this is just so fantastic, Rohan. It's really wonderful. Going back, you had a plot where you were showing, I guess in my mind, it was what a projection would look like of the stars in your, I guess you call it I forget the initials now, but anyway, your sausage and the ones that you're simulating. And it was asymmetric. There seemed to be more in the south. And that makes sense to me anyway, that it would not be continuous across the middle, because after all, things spend more time at the extremities of their orbit. But that asymmetry, I suppose, would be reflected, or this is the question, in a dark matter asymmetry. And
that is,
just comment on it.
Yeah, no, that's a very you've honed in on a very cool detail that I'm trying to think about as well right now, right? So like the reason you get that asymmetry again goes back to the orbit, right? So when you plunge into the galaxy and you rise, so when you follow this trajectory, right, and you rise above the plane and then fall back again. So this is not a good plot to look at this, because this is XY, and what we really want is in the Z plane. And the asymmetry comes out because your penultimate apocenter is deeper than your final apocenter. So you do get, so that asymmetry is really like a very physical thing that we expect. So you end up with the Hercules Aquila cloud being more massive than the Virgo overdensity. And this is something that is not observationally constrained right now, and something I'm trying to work on, because that would be super cool. Because if we measured the relative mass of each of these overdensities, we could back out the exact phase of the orbit that the collective debris is in. And so that would be a very, very cool constraint to place on this whole matter. And then indeed, correspondingly in the dark matter as well, you would expect there to be this slight asymmetry, but I would not expect it to be as pronounced, because the dark matter is stripped, I would say, at larger radii. And yeah, I'll say that, yes, I would expect asymmetry, but not to be as pronounced as in the stars. In general, like the shape of the stars is more colder than the shape of the dark matter that has a more like slightly more settled nature. But no, thank you. That is a very, that's a point I was very excited about in this paper, but I didn't have room to discuss it. But that is something we can do in the future for sure. Basically measure the masses of each of these overdensities to really get at what phase of the orbit we are in, and to confirm this picture in general that it did come in from under the plane.
Cool. No one else has spoken up. I will ask one last question, which is, Rohan, now you've showed how much you really gained from these beautiful surveys with your more than 150,000 spectra, right? So I'm just curious, this is kind of beyond your field, but what are your hopes for external halos and learning about accretion events in more details with Euclid and Rubin and Roman? Is that something you're thinking about, where we clearly won't have the kinematics that you have to really do all these fine detailed plots, but have you thought more about what we might learn from those or about those?
Not in as much detail as you have, but it depends on what kind of question you're trying to answer, I think. Like if you're trying to get at tests of CDM on a high level, which is like the conclusion that we reached here, which was that the bulk of your stellar halo must come from a handful of events. So like a handful of fairly massive dwarf galaxies on average. I can see us being able to test that on some level, because you would expect these fairly massive mergers, my work is showing, even when they're so old, right? There's a 10 giga-year-old merger and you're seeing these very pronounced overdensities. I would say that maybe there is hope of getting at these large scale features to try and add support to that kind of idea. But yeah, beyond that very broad level, I haven't thought too much about what else we could learn.
No, but that would be really cool. Okay, so we're running out of time. Thank you so much, Rohan, for an incredible talk. We're very glad you could join us. And thanks everyone for joining in the room and on Zoom. Bye.
Thanks, everyone. Cheers.
Yeah, let's thank him one more time. Sorry, I forgot that part. Cool.